Welcome back to The Explainer. I'm so incredibly thrilled you're here today because we are tackling a concept that is an absolute game changer for anyone writing software. We're looking at abstract data types, or ADTs. Look, if you've ever felt completely bogged down by the sheer mechanics of memory management when you're really just trying to map out a program, well, mastering this concept is going to completely change how you plan your code. It's all about stepping back and looking at the big picture before you get your hands dirty.
Okay, let's dive into this. We've got a really solid roadmap for today. We're going to start by defining the ADT rulebook, untangle the core difference between ADTs and data structures, meet the common ones you need to know, explore exactly why we even use them, and finally, we'll put it all into practice. Let's get going.
Kicking things off with Section 1, the ADT rulebook. Let's talk about the high-level description. So an abstract data type, or ADT, is fundamentally a high-level description. It defines a type of data strictly by its behavior. It tells us what values can be stored and what operations are allowed. Things like adding or removing an item. But here's the absolute best part. It intentionally leaves out the low-level memory details. It completely hides them. It doesn't force one fixed implementation method on you at all. Different programmers can implement the exact same ADT in completely different ways, and the ADT honestly doesn't mind one bit. I love the metaphor we're looking at here. Think of an ADT as a rule book. It tells us what the structure must do, but not exactly how the code must build it. Literally, if you take just one single thing away from today, make it this. The rulebook absolutely does not care if you write your code with arrays, pointers, or sheer magic. As long as you play by its behavioral rules, you've successfully created that ADT.
Let's quickly run through its 4 defining properties. 1, it stores data. Pretty straightforward. 2, it defines operations. It tells you exactly what you're allowed to do, like a push or a pop. 3, and this is that magic trick of abstraction I mentioned, it hides the implementation. You just deal with the behavior. All the messy, complicated memory details, safely tucked away under the hood. And 4, because of that hidden nature, it supports multiple implementations. You can totally tweak how it's built later, depending on if you need raw speed or to save memory.
Moving right along to Section 2, ADTs versus data structures. This is the classic what versus how.
Okay, this is where students usually get tripped up. The big divide between what a structure does and how it's built. Think of the ADT as the what. Take a stack, for example. A stack simply says, hey, whatever goes in last comes out first. That's it. Conversely, the concrete data structure is the how. This specifies how the structure actually lives in the computer's memory. We're talking pointers, resizing, contiguous layouts. So a stack is an ADT, while an array-based stack is just one specific concrete way to execute that rulebook.
Let's see this in action. Both of these implementations follow the exact same last-in, first-out rulebook. But man, look at how differently they're built in the computer's memory. The array-based stack uses indexed positions. It's super fast to grab the top element, sure, but if it gets full, you have to deal with resizing the whole thing. A linked list stack, though, it uses nodes and links. It grows organically without needing a massive block of continuous space, even if it uses a tiny bit more memory per node. 2 totally different biological makeups, pulling off the exact same abstract behavior.
All right, Section 3. It's time to meet the common ADTs, your core roster.
Let's walk through the main behaviors you absolutely need to recognize. First up, the list ADT. Its whole purpose is to store an ordered collection using operations like add, remove, and traverse. Next is the stack, which we just talked about. It's strictly LIFO, last in, first out, with its push, pop, and peek operations. Then we've got the queue. Think FIFO here, first in, first out. You enqueue items to the back, dequeue them from the front. And finally, the tree ADT. This one stores data in a hierarchy rather than a straight line, relying on insert, remove, and search. Now pause for a second. Notice how not a single word here mentions arrays or memory pointers. It is 100% pure behavior.
Which brings us to Section 4, why use ADTs? Let's talk about the incredible benefits of abstraction.
So why do we even bother with this extra layer? Well, first, clear design. You can plan and decompose a problem's behavior before getting hopelessly bogged down in low-level details. Second, reusable thinking. Once you define a queue, you can use that exact same conceptual logic for a printer spooler, a task scheduler, or a traffic simulation. Third is flexibility. You can choose the best concrete implementation later on. And finally, and honestly this might be the most important, teamwork. Because of abstraction, your teammates can use your structure just by calling its operations.
They don't ever need to understand the absolute memory nightmare you might have written to build it. It keeps the whole system modular and easy to maintain.
Now, I gotta pause here because this misunderstanding happens all the time. People will say, oh, an ADT is just the same thing as a data structure. Or they kind of assume an ADT only has one correct way to be built. But the stark truth is, the ADT is just the abstract behavior, while the data structure is the concrete implementation. You can have a dozen totally different code implementations that'll perfectly satisfy the exact same ADT rules.
Let's move to our final section and see how this builds into actionable skills. Section 5, put it into practice.
Okay, you're in the hot seat now. Imagine you're building a school app to manage the order of students waiting for help at an IT desk. Students join at the back of the line, and the student at the very front gets helped first. Based on the rulebooks we just covered, which ADT best matches this behavior? Take a quick second to think about it.
Did you get it? The answer is a QADT. It is the absolutely perfect fit because the first student to arrive should be the first one helped. Classic first in, first out behavior. And notice the methodology here. We chose the ADT by matching its behavior to the problem first. We did this way before we even thought about whether to use an array or a linked list to actually code the app.
To really lock this concept in, let's cleanly separate these ideas. Notice how statements like a stack uses push and pop or a tree stores data in a hierarchy sit firmly in the ADT column. They describe operations. But the second you start talking about building a queue with a circular array or storing the top element at index 0, you have officially crossed the line into implementation details.
Now, if you're taking an exam on this anytime soon, I want you to memorize this exact phrase. The ADT is appropriate because its operations match the required behavior of the problem. This is a golden ticket right here. If you use this phrasing, you are showing the examiner that you truly grasp the abstract idea first before discussing how it's built in memory.
So here's our final concise summary. The core takeaway to burn into your brain today. ADT equals what the structure does. Implementation equals how the structure is built. It's the rulebook versus the execution.
And that brings us to the end of today's explainer. I want to leave you with a quick thought to ponder as you continue your programming journey. Next time you sit down to code a seriously complex problem, are you going to immediately start wrestling with memory blocks and arrays? Or will you step back, define the behavior, and write the rulebook first? Thanks so much for hanging out with me on the explainer today, and hey, happy coding!